Hello and welcome to our first video of our Calculus 1 class. Today we're going to kind of do an overview of a lot of the stuff that's coming for a good chunk of the semester. And in particular we're looking at an introduction to the derivative. So we're going to look at that via the slope of secant lines, tangent lines, and how that relates to instantaneous speed. Okay, so let's dive in. So a big chunk of calculus deals with one fairly simple question. How do we compute the slope of a curve, so not necessarily a straight line, but a curve at a point? And to sort of build up that answer, we're going to look at the slope that we do know, the slope of a straight line. So we start with the slope of a straight line and try and get from that to a curve. Okay, and to start with that question, let's take an incredibly simple example. If I travel 60 miles in 1 hour, how fast did I go? Well, the average speed is simply the change in distance divided by the change in time, so 60 divided by 1, 60 miles an hour. But of course, notice that's the average speed. It doesn't capture the speed at any particular point. It's the average speed over that whole chunk of time. And of course, in math, we can think of that as being similar as the slope. We've got to find the slope of a curve, so an average how much a curve has gone up. We take the change in y divided by the change in x. You might have seen this as rise over run. Okay, so just to sort of remind ourselves of how that goes, let's warm up with the equation of a line. So we've got 2 points and we want to find the equation of a straight line through those 2 points. So my 2 points are 2, 4 and 7, 8. So remember to find the slope, so that's that rise over run, we take the second y value minus the first y value, that's the numerator, and then the second x minus the first x, that's the denominator, and that gives us 4 over 5, and that gives us a slope of the line. And from that we can use the point slope form, so the y minus y point equals m, the slope, times by x minus the x point, and that gives the point slope form of a line. So I've used the point, the 2, 4 point here, this point, but you can actually use either of these points and it will give you the same equation. And so the equation of our line is y minus 4 equals 4/5 x minus 2. Do notice often we have a straight line as being of the form y equals mx plus b. But for what we're going to do, actually this point slope form is a little more useful, I suppose. But lines are easy. Lines are easy, straight lines, because their slopes do not change. Curves are more difficult because their slopes do change. Okay, and that's what we're going to get at now. So before we do that, let's just sort of define a couple of lines we're interested in. So a line between 2 points on a curve, so in this case the secant line there, it goes between the points P and Q. So that's called a secant line because it crosses twice. If you imagine a line that just touches the curve at exactly 1 point, that's called a tangent line. And what we're going to look at is how we get from the secant line to the tangent line. Okay, so we have a secant line, so we know it goes through these 2 points, P and Q. The slope of the secant line, well, it's exactly the thing we just talked about, finding the slope of a line. y2 minus y1 divided by x2 minus x1, and that's the m, the slope of that line PQ. And if that's the slope of the line PQ, the equation of that same line is, again, just as we showed previously, this point slope y minus y1 equals m x minus x1. Okay. Well, the tangent line should have a very similar slope. We've got our point x1, y1, and we have our slope mp. Well, we can use the same equation, but how do we find the mp? And of course, that's the key. That's what we're looking at now. How do we find the mp if we only have 1 point to use? Okay, and that's the thing we're going to be using on. And the kind of the idea, and of course we'll look at this in just a second, the idea is that we use a point Q that's quite close to P. We can compute the secant slope, and then we move that Q closer and closer to P and see what our slope is heading towards. We take what's called a limit there. Okay, so let's go ahead and sort of try and look at an example of this. So our function is going to be y equals x cubed, and the point we're interested in is x equals 2. So we're trying to find the slope of the function x cubed at the point 2, x equals 2. So given the actual point is 2 and then 2 cubed, so in other words 2, 8. And given that, we can take another point, in this case we called it kind of x2, y2, to find an estimate for that tangent slope. Okay, so let's go ahead and do that. So if we take x1 is just fixed, right? That's the point we're interested in, that 2. x2, we're going to take it to be points close to 2. Okay, so what are some numbers close to 2? Well, 1.9 is pretty close to 2. 1.99 is even closer. And that's on the what we might call the negative side, the side where the points are a bit less than 2. We could also look at the points that are a bit more than 2, so 2.05, 2.01. Again, they're getting closer and closer to 2. And in both these cases, sort of here and then again here, we can kind of look what those values are heading towards, and it looks like those numbers are heading towards the value 12. Right, 11.41, 11.94, that's getting pretty close to 12. From the other side, 12.03, 12.3, 12.06, that looks to be heading towards 12 as well. So of course that's not perfect, but numerically it looks like that's what our slope is heading to be. Let's try one more time. What if our function is 2 to the x at x equals 1? So take exactly the same thing. We take the secant slope, so our point is 1 and 2 to the 1. Well, that's just 1, 2. And then our other point is x2 and then 2 to the x2. Again, we can take these x2 values, 0.9, 0.99. And now have it sort of heading towards 1, right? 1 is in between here. 1.1, 1.01 heads towards 1. 0.9, 0.99 heads towards 1. So we have to look at what these values seem to be heading towards. Well, it's certainly going to be 1.3 something. I don't know, maybe halfway between these two is about 1.386. Okay, and again, it's just an estimate, but it's not a bad estimate for what we think the slope will be to the function 2 to the x at the point x equals 1. Okay, and so from that, we did that for specific points and specific functions. We're going to build the derivative function. Okay, so we're going to take our point P just as we did previously to be x1 and then f of x1. That's our fixed point. And then we're going to choose a point Q that's going to be a little bit away from x1. And in particular, we're going to say it's h away, right? So it's just this little distance h away from x1. So therefore, this is our x point. We take f of x1 plus h to be our y point. But with this point, we can't take the h to be 0, because then Q and P would just be the same point. And again, we'd have that problem of not having a slope. Okay, so now, well, we take the secant slope. We take the y value minus the y value, so the higher y value here minus the lower y value here. On the bottom, we take the two x values and subtract, but this x value minus this x value is x1 plus h minus x1, and of course the x1s just cancel. So all we're left with is, on the bottom here, is just an h. And as h gets close to 0, this whole function should approach the tangent slope. Okay, so that's our m, if you like, our slope, but simplified down, and we take that h to get closer and closer to 0. And so in particular, what we're talking about is we're taking a limit. We're taking the limit of that function as h approaches 0. And at this point, we've specified a point C. So the derivative of the function f at the point C is given by this whole thing as h goes to 0. Okay, and that's the slope of the tangent line to the function at that point C, f of C. Oh yeah, and of course, so once we've got that slope, we want the actual tangent line, not just the slope of the tangent line, we do just as we did previously, take the point slope, formula with the CF of C and F prime of C. Okay, so it's still changing y with change of x, but it's harder because to take it as a point, well, we need to take the h to be, well, we can't take the h to be 0, so we take the limit as h approaches 0. Okay, so let's take one quick example of this. Here's our function, and I've kind of based this on the Oblivion ride. It's a ride at Alton Towers in England that I used to go on. And we want to know what is the speed that we're traveling at the time t equals 2. In other words, what's the instantaneous rate of change at 2? So just as we did previously, we can take kind of an average. So how fast are we going from 0 to 2? And notice we're going down, right? It's a roller coaster ride, so we start off going down. So we're going to get about minus 32 feet per second from our average from 0 to 2. From 1 to 2, we're going at minus 48 meters per second. Then we can maybe look on the other side of 2, right? These are the numbers that are a bit bigger than 2. From 2 to 3, our average velocity is minus 80. Then from 2 to 2.5, minus 72, minus 65, minus 64.16. It appears that our exact velocity, our instantaneous velocity at 2 is about minus 64 feet per second. Okay, but again, that's just numerical, it's not perfect. But instead, we can actually use the formula we just talked about. Okay, so this is this formula. If we just go back a little bit, right here, this thing we thought to be the derivative. Limit as h approaches 0, f of c plus h minus f of c over h. That's exactly what we're doing here. We've got the point 2. So we have 2 plus h, we have f of 2 dividing by h. We plug it into the function. Remember the function was minus 16t squared plus 150. So we plug everything into minus 16t squared plus 150 here and here. And once we've reached this stage, it's really just a question in algebra. Okay, the calculus is kind of done. We just have to simplify basically. So we can FOIL out that 2 plus h squared. We can maybe distribute this 16. So 16 times 4 is 64. Distribute the negatives and positives and so on and so on. And we get to this point. And then things start cancelling. And in fact, you can kind of already see the 150 plus 150 and minus 150 are going to cancel. Minus 64 plus 64, they're going to cancel. And so we're not actually going to be left with very much. We're left with minus 64h minus 16h squared. And this is what we're really looking for. If we can get to the point where we can cancel out the h's, that problem of having that h, that 0 in the denominator, kind of goes away. And that's exactly what happens as we go to here. We cancel out the h's, and because there's an h in both terms here, it cancels in both places. And we're left with minus 64 minus 16h, and of course this is easy. As h goes to 0, this piece just disappears. So we're just left with minus 64, and again that's what we guessed when we did this numerically. The velocity at time equals 2 is minus 64 feet per second. Okay, we've gone through that pretty quickly, but that's okay. This is just an introduction. We're going to focus on all of this in a lot more detail as we're going along. Some things to remember. So the secant slope is the average rate of change, right? That line that crosses through the curve twice. The tangent slope is the instantaneous rate of change, and that's the line that just touches the curve. The derivative gives the tangent slope, given by this formula right here, and the tangent line is given by this. So we take the point slope equation for a straight line, and using as our m this derivative we just found. Okay, that's it for our first lecture. Thank you.